Hello, and welcome to today's webinar, Integration of Field Data into Numerical Modeling for Slope Stability Assessment, presented by Dr. Navid Barani, Senior Geomechanics Engineer at Itasca, North America. In this session, Navid will discuss how field data can be effectively integrated into numerical modeling workflows to improve slope stability assessments, reduce uncertainty, and support more informed engineering decisions. Following the presentation, Navid will be joined for a live discussion and Q&A by Ryan Peterson, Senior Geotechnical Engineer and Consulting Manager, as well as Christian Cancino, Senior Geomechanics Engineer with Itasca North America. If you have any questions during the presentation, please go ahead and add those to the Q&A. We'll take those questions and answer those right after the video. Thank you very much and enjoy the show.
Hello everyone. Thank you for attending this webinar. Today I'm going to discuss the integration and analysis of field data, including prisms, radar, and water pressure into 3D numerical models for slope stability assessment. This webinar consists of two main parts. The first part is a presentation where I briefly discuss the importance of incorporating field data into numerical models for model calibration. In the second part, I will show you how we can use IMAT to import such data, create plots, and analyze them. The focus of this presentation is on open pit mines where slope stability is a critical concern. The main objective is to bring together field monitoring data and integrate them directly into numerical models. The approach we use is to explicitly simulate major geological structures. Then we calibrate the model by matching the simulated rock block movement, for example a wedge, with what was observed in the field. At Itasca, we have several tools for this purpose. In this presentation, the focus is on FLAC3D for model calibration and IMAT for data integration and interpretation. Let me briefly go over the numerical programs we often use for slope stability projects. Let's start with IMAT. IMAT stands for Itasca's Mining Analysis Toolbox. It's essentially a set of pre- and post-processing tools built around FLAC3D, but tailored specifically for mine scale problems. One of its advantages is that it simplifies the workflow and makes it easier to handle large data sets and model setups through a more user-friendly interface. On the numerical modeling side, everything is based on FLAC3D, which is a continuum-based program. What's important here is that it allows us to incorporate geological structures explicitly into the numerical model. So for example, structures can be represented implicitly using ubiquitous joints or explicitly using interfaces or zone joints. In terms of material behavior, both zone joints and interfaces follow a linear Coulomb shear strength criterion. That means that the model is governed by parameters such as cohesion, friction angle, tensile strength, as well as normal and shear stiffnesses. Through model calibration, we often adjust these parameters to be able to match modeling results with field observation. Here I'll show you a case study where we applied this workflow to an open pit mine. The main goal was to use field data for both model calibration and predictive analysis. What you see here are examples of how IMAT helps bring different types of field data together in one place for visualization and data interpretation. For example, we have prism monitoring data, which gives us point-based displacement measurements over time. This is really useful for tracking localized movement of the slope. We also use radar data, which provides much higher spatial coverage, so we can use the formation patterns across larger areas of the slope and identify zones of acceleration. And finally, we incorporate water pressure data, which is critical because it directly influences effective stress and slope movement and stability. By combining all these data sets, we can calibrate the model in a much more robust way and ensure it reflects the actual field conditions. Now let's talk about model calibration. The goal is to match observed field behavior based on collected field data and use the calibrated model to predict future excavations and rock mass responses. For a project that I'm showing you here, we used FLAC3D to match field data by adjusting the properties of major geological structures that form a wedge. We used the zone join logic to represent these structures. The properties that we used were friction angle, both peak and residual values, and the normal and shear stiffnesses. We found that these parameters have a strong impact on the movement of the wedge. And for model calibration, we use two different approaches, qualitative and quantitative approaches. From a qualitative perspective, we compared the overall displacement pattern from the model with the radar data. So we were looking at whether the model captures the same wedge movement and general deformation trends. Then on the qualitative side, we compared the modeled horizontal displacement directly with prism measurements located within the wedge. This includes both individual prism displacement and the average displacement across multiple points inside the wedge. As I mentioned earlier, water pressure is an important parameter affecting slope behavior. We often receive data in the form of water pressure grids or phreatic surfaces. Here, I'm showing you a cross-section of the FLAC3D model under three different scenarios. In all cases, the groundwater condition is represented below the phreatic surface. But the key difference between the models is the RU value. So RU is the pore pressure ratio. It is a simplified way to represent the level of water pressure relative to the total stress. It is often used to account for elevated water pressure conditions caused by heavy rainfall or snowmelt in slope stability analysis. So here we look at three cases, RU equal to 0, 0.1, and 0.2. So when RU is 0, we essentially have no additional water pressure contribution beyond the defined water table. As we increase RU, we are introducing higher water pressures within the rock mass, which then reduces effective stress and therefore has a direct impact on stability and deformation of the slope. Now, after this short presentation, I'm going to show you how we can use IMAT to integrate and manage field data, including prisms, radar, and water pressure. But before starting IMAT, let me quickly go over the project folder and the data that we have. The main project folder consists of 5 subfolders, as you see here, and each contains one or more data files. Under hydro, we have the water pressure data, which is a text file. In prisms, we have a CSV file, which contains data for 4 prisms. In the radar subfolder, there is a CSV file. The structures subfolder contains 3 DXF files for 2 faults and 1 weak layer, which forms a wedge. And in the topo subfolder, there is a DXF file. Now let's start IMAT. All right, when we start IMAT, we have 2 options. we can either open a recent project or create a new IMAT project. Today we are going to create a new project. First, we need to specify the project name. Let's call it Slope Stability Assessment -demo. Then call the mine name OpenPit Mine. The project folder location is the folder where all the data files are located, and the new files will be saved. The mine reference system is east, north, up, which represent X, Y, Z, and the unit system is metric. Now let me first give a brief overview of the IMAT user interface. On the left-hand side, we have the Project Explorer window, which consists of a series of plugins. For example, we have geometries, block models, FLAC3D underground, and so forth. As we pick different plugins, the available properties, the information about that plugin, and its controls are all adjusted. On the right-hand side, we have the viewer, where we can see the geometries, mesh, results, and so forth. And down here, we have controls for presenting the information as to what IMAT is doing, output, and its communication with FLAC3D. Today we are going to use the Geometries plugin to import the pit topography, the structures including the two faults and a weak layer, and the radar data. Then we are going to use the block models plugin to bring in the water pressure files, and we are going to use the field data for prisms. Let's expand the Geometries plugin. Here we see that we have different folders. Select pit shells, right-click, import geometries. Let's go to the topo folder and select the DXF file. Here we can convert file data. For example, we can change the reference system, the unit of the length. We can move the coordinates if needed, but we don't want to change anything here. Let's expand the pit shells subfolder, select the topo DXF file. We see that it's about 64 megabytes. We can convert it to an STL file. Select extract geometries, remove points and lines so that we only have wireframe. Let's delete the original DXF geometry. And now we see that we have an STL file which is only 4 megabytes. Let's turn on the light bulb, then go to the viewer and zoom extend so that we can see the topography. Here we see that the slope consists of several benches and a ramp over here. The next step is to bring in the structures. So right click, select import geometries, and then go to the structures folder. Select the two faults and the weak layer. Again, we can convert file data, but we don't want to do it. And here you see that the structures are imported. They are relatively small, so we do not need to convert them to STL. Let's turn on the light bulb to be able to see the structures. Here you see that we have one fault over here, another fault, and a weak layer at the bottom, which create a three-sided wedge. Let's change the colors of the structures. Go to the properties and select an arbitrary color. Here I'm going to go with light gray for the two faults and a darker gray for the weak layer. The next step is to bring in prism data and create some new plots. When you expand it, you see three options. One of them is prisms. Select it, right click to create a new data set. Let's call it prisms. Then expand the prisms subfolder, select it, select import prisms to be able to import the CSV file. Let's go to the prism subfolder, open it, and select the CSV file. Here we see the first 6 rows of the CSV file. The first column is prism name, the second one is the date, third one is easting, then we have northing and elevation. So we need to update the column name, data type, and time format. Select the first column. The column name is ID, and the data type is label. The second column is date or time. The data type is again date or time, and then we need to change the time format. Here you see that we have month, day, and year. So we change the time format to month/day/year. Then select the third column, which is easting. So column name should be X, and the data type is number. For the next column, change it to Y, and the last one is elevation or Z. Everything looks good here. Click OK. We do not want to change anything in the prism measurement data. So we go with no here. We do not want to change the data file. And done. The prisms are imported. Let's turn on the light bulb to be able to see the prism location. Here we can increase the prism size. Go to the properties, increase the prism size from 5 to 15. We can show prisms labels. Let's increase the size of the label from 15 to 25. Now we can easily see them. So there are 4 of them from P1 to P4. Let's click on prism number 2. Let's expand the information section. Here we see that we have the coordinates of prism, the x, y, z of the selected point, which is the prism number 2. We have a plot here, which is displacement versus time. So we see that data started from beginning of September, and we have data for 2 months until the end of October. Here we have different components of displacement. We have the vertical component, the horizontal component, as well as the total component. The next plot, which is very useful, is the Wonder plot, which shows the changes in the y direction as well as the changes in the x direction. The first reading is 0, 0. So we see that lighter color indicates initial readings and darker color indicates later readings. So we see that there are some data points on the left-hand side and there are some data points on the right-hand side, and that suggests that there is some noise in the data. The maximum displacement in the x direction or easting is 10 millimeters. So that means that we are within the range of the error for prisms. So this suggests that this part of the slope, which is on the right-hand side of the wedge, is not moving. Now let's select P1, which is right in the center of the wedge. Let's first find the first reading, which is here, and we see that pretty much all the data points are to the right of the first reading, indicating that the prism is moving to the east or into the pit. And you see that the maximum displacement is about 50 millimeters. And now let's select another prism, which is prism 4. Let's find the first reading, which is 0, 0 here. And again, we see some data points to the left of the first reading, and there are more data points to the right, which indicates that this part of the slope is also moving to the east, but the magnitude is about 20 millimeters, which is smaller than prism number 1 right in the middle of the wedge. Now the next step is to bring in the radar data. So we need to go to geometries, create a new subfolder, and call it radar. Here you see that the subfolder radar is created. Let's right click, import, and since it's a point cloud, we select CSV point data. Let's go to the radar folder and select the CSV file. Again, here we see the first 6 rows and the column. The first column is easting, next one is northing, and then we have elevation. Then we have displacement magnitude and cell ID. So let's first select the first column, change the column name to X. The format is number. The second and the third one are Y and Z. Column number 4 is displacement magnitude in millimeters, and the type is number. You do not need to select the last one. Everything looks good. Click OK. And here we see that the radar data, which is a point cloud, has been imported. Let's turn it on. Now we see all the data points. We are going to increase the size of these points and color code it. Expand the radar folder, select the displacement. Let's go to properties. Here we want to give a fixed color range, but first let's increase the point size from 2 to 5. Then let's go back to the properties, check the fixed color range option. The minimum value is minus 100 millimeters and the maximum is 0. So a negative number indicates movement into the pit. We can also change the color map. I would like to go with AMP and select the step color map. Make sure that they are divided into 10 steps, and then reverse the color map so that darker color indicates larger displacement magnitudes and lighter color indicates smaller displacement. So here we clearly see that the wedge experiences larger displacement than the rest of the rock mass. And we also see that the left-hand side of the wedge has displaced more than the right-hand side. However, the overall displacement seems to range between 40 and 60 millimeters, which is consistent with prism number 1 that we looked at earlier. In the last part of this webinar, we are going to use the block models plugin to bring in the water pressure data. Select it, right click, and import the block model. Let's go to the hydro folder and change the file type from CSV to all files so that we can see our pore pressure data file. As you can see, it's a text file. Open it. Now we need to change the delimiter from comma to space to be able to see all the columns. Select the first column. It's easting, select X. The second column is Y. The third one is the elevation or Z. And the last column is the water pressure data in pascals. Let's select define custom name and call it water pressure. Everything looks good. Hit OK. And give the model name. Let's call it WP, representing water pressure. The size of the block model is 5 by 5 by 5. And let's go with the default cutoff search distance of 50. We don't want to convert the data file. Now we have to wait so that the water pressure data file is imported. After a few seconds, we see that the calculated grid contains over 46 million points. The file is imported. Let's expand the block models plugin and the water pressure model. Turn on the light bulb so that we see all the data points. Now turn on the water pressure subfolder so that we can see the cutting plane showing the water pressure contour. Now first we need to remove all other files that we have exported, including the structures, radar, and prisms. We can easily click on the corresponding geometry in the IMAT viewer legend to remove them. So here I'm removing the prism data. Now we only have the topography and the cutting plane for the water pressure. Let's go to properties and select fixed color range. The minimum is 0 and the maximum is 10 MPa. Next, check the step color map. Make sure there are 10 steps, which shows the increase in water pressure from 0 to 10 MPa. So now we see a cutting plane. We can easily move this cutting plane along the slope using the mouse wheel. So we need to go to controls and in the translate use the mouse wheel to move the cutting plane. And this way we can evaluate the quality of the data. So here we see that there are some areas where water pressure is non-zero at and above the topography. And that means that at this point we should get back to our client to ask for a revised pressure, or we can actually remove the non-zero water pressure in IMAT after we create the grid for the model. And that brings us to the end of this webinar. Thank you for your attention. I hope this session gave you a good overview of how we integrate field data into numerical modeling and how tools like IMAT can support that process. Now, I'd be happy to take any questions.
Thank you, Navid. So, anyone that has questions can feel free and jump in and start writing in the chat your questions. In the meantime, let me just pull up an image here for you to look at. So it's just on a black screen. Okay, we have a couple of questions coming in on the chat. First one is, thanks for the presentation. Would you please explain about the data set you imported into IMAT? For example, how did you collect weak layers based on field investigations? Also, can we connect to remote sensing data as well?
Hello, this is Navid Barani. Thank you for your question. So in this project and in projects like this, we usually receive structural models from our clients. So they provide us with the geometries, in this case, the weak layer, and other structures, and then we import them into our model to be able to represent them. I hope I was able to answer this question. And the second part, can we connect to remote sensing data as well? I'm not sure about this question. If you could elaborate more what you mean by that.
Okay, we'll give them time to go ahead and respond to that. Another question came in. Thank you again for the presentation, but they go on and say, how can we add the borehole and simulate the water pressure drawn down?
If I understand this question, as you saw in the field data plugin, there are different options. One of them is borehole, and you can basically import any type of data that you have along boreholes in your data set. In terms of water pressure drawdown, so again, here we create the pore pressure grid based on the data that we have. So that has to be built in before we import them into the IMAT. If we have phreatic surface, we can import phreatic surface and then create the pore pressure grid. But if we have data from boreholes, first we need to create the pore pressure grid outside the software, and then we can import them into the software for further analysis.
Thank you, Navid. I should also note, joining us in the webinar here for the Q&A is Ryan Peterson, Senior Geotechnical Engineer and Consulting Manager, as well as Christian Cancino, Senior Geomechanics Engineer for Itasca, North America. Welcome to the Q&A, gentlemen. Okay, another question has been submitted. After all information is in IMAT, what happens? And by that, they add, what can we do with IMAT?
Yeah, that's a good question. So IMAT is Itasca's mining analysis toolbox. The engine is FLAC3D. So you can basically create a FLAC3D model using IMAT. It works based on octree zone, meaning that all the zones are cubes. We can build that model entirely in IMAT, and we can import any kind of data. We can adjust the properties to calibrate the model based on field data, and we can analyze the data. So everything that you can do in FLAC3D, you can do pretty much in IMAT as well.
Terrific. Thank you, Navid. Okay, another question that has been submitted. You seem to only bring the structures in as geometries for viewing. Can you explain your preferred approach to build the structures into a FLAC3D model for analysis?
So there are different ways that we can include structures in whether it's FLAC3D or IMAT. If, let's say, we want to represent an isotropy, let's say bedding planes, we can use an implicit approach such as ubiquitous joints. For ubiquitous joints, what we need is the properties, the strength properties of the joints as well as their orientation. We don't need to have the stiffness properties. If we want to represent specific faults or structures, there are different options. In the past, we would use interface to represent joints. Since FLAC3D version 9, we can represent them using zone joints. So we can create the geometries in another software such as Gridle and import the geometries as well as the Gridle mesh into IMAT or FLAC3D for further analysis.
Good, thanks. All right, Ryan, Christian, do you have anything to add?
Yeah, this is Christian Cancino. So the structures, I would say the preferred way to do it is explicitly simulating as a surface that can sleep and separate. That's the most accurate representation of a discontinuity. Even though when FLAC3D, the engine behind IMAT, is a continuum model, there are ways to put faults explicitly, as you may know, the all interfaces or the new zone joint logic. So that will be the preferred way to do it. And you can do it by building the model grid in Griddle, as Navid was mentioning, or a different meshing software, and then bringing that to either IMAT or FLAC3D directly, right?
Thank you, Christian. Okay, another question has been submitted. Again, thanking Dr. Barani for his great presentation, but they have two questions in regards to the IMAT workflow. First off, for the topography, is the standard pipeline still relying on Rhino and Griddle to generate and import the mesh geometry, like the topo.stl we see in the Project Explorer into IMAT, or is there a more direct workflow now?
We can import the geometries as long as we have the files like the DXF files. We can import them into IMAT or FLAC3D. In terms of meshing, we can create, as I mentioned, arc-tree zones, and then we can use the topographies to delete or null the zones above the topography, and this way we can have the topography in the model. That would be my answer if I understand the question, but maybe Christian can add more to it.
Sales and marketing will jump in here. There are multiple different ways to actually import geometries into IMAT. If you'd like to learn more, we can email you and set up a call afterwards. Another question related to this first one, regarding the satellite monitoring. Does IMAT natively support the import of SAR and InSAR displacement data? I noticed the radar, quote unquote, section with PTS files for displacement. So I assume InSAR datasets could be integrated there as well.
Yeah, I think we need to look at what data types are supported in IMAT. This is something I don't have the answer on top of my head. We can double check and see what other file formats we can import in, and we can get back to you.
Yeah. I would add to that from a sales and marketing perspective, we have multiple different ways of importing geometries. We have had clients that have worked with SAR data in the past. It's all about massaging the data to meet the format. We're happy to set up a call afterwards to discuss that if you like. Okay. This question comes from Luigi. Luigi asks, can IMAT handle the structures directly now? Navid?
Well, if we want to, let's say, represent a fault zone, we can create a weak zone to represent the fault, which consists of a few zones across the fault. But for structures, we need to create the geometry and the mesh in, let's say, Griddle, and then import them into IMAT. We are working on developing a workflow to be able to create structures in IMAT, and our developer, Heist Basson, is working on it, and he has a presentation in the upcoming Slope Stability Conference in Lima. So I would suggest to contact him, or if you would like, we can connect you with him.
Yeah, I would just add to that, Luigi, thank you. More than happy to talk about the future development, and we can set up a call to show you exactly what we're doing there.
Yeah, I wouldn't add that IMAT purpose is not only handling faults, right? So it's just a friendly GUI with the powerful FLAC3D engine behind that, right? So that's for one specific case in a continuum model, right, Luigi? There are ways to deal with that. In the meantime, we have to rely on Griddle or an external remeasure. And as Navid said, we're working towards that specific problem of handling faults directly in IMAT to build these explicit faults, but that's still under development, and we'll let you know if we have some improvements in that area.
Okay, we're coming up at about 15 minutes to the hour. I would like to ask if you have any additional questions, to add those to the chat now. Just pause there for a moment. All right, another question has been submitted. Is IMAT also connected to 3DEC?
I'll
go ahead and answer.
Yeah, go ahead.
Yeah, I can answer that, Navid. No, it is not. Although IMAT is based on FLAC3D and comes with all of the FLAC3D options, is not a we are not leveraging 3DEC at this time. And we'll give another 30 seconds or so. Okay, I don't see any other questions coming in. Oh, there we go. As soon as I said it, another question came in. All right, can we do the mesh in IMAT? Navid, I'll let you answer that.
Yeah, you can create octree zones, basically hexahedral zones in IMAT directly. But if you have, let's say, several structures, then you need to rely on another software like Gridle to create the geometry and mesh, and then import them into IMAT.
Thank you, Navid. Okay. Another question has been submitted. Again, great presentation. Thank you, Navid. Can we also implement and model structures such as rock bolts and liners in IMAT?
I believe that those are not implemented yet.
I would just jump in from my experience having sat in on calls in the past. You can build your model in IMAT and then pivot and import and structure such structures in FLAC3D. IMAT is a overlay, if you will, for FLAC3D. So anything you can do in FLAC3D, you can also do in IMAT. Okay, Luigi had another question. Thanks all. It's nice to see the development of IMAT. I've been using it for, I will be using it in the coming years, and we'll be talking to some of your friends soon. Okay, that was not a question. One last moment for questions from the field. Right. So it looks like that is a wrap. I'd like to thank everybody for attending today's webinar, Integrating Field Data into Numerical Modeling for Slope Stability. We hope you found the insights transforming geological and geotechnical data into reliable numerical models valuable to your engineering projects. If you have questions regarding today's webinar for the technical concepts presented or our engineering software, please feel free and email us at info@itascainternational.com. Also, one last note, we are hiring globally. Itasca is expanding, and we are looking for talented individuals to join our team of global experts. We currently have open opportunities across our international office locations. For a complete list of open positions, please visit our careers page. Thank you once again. And on behalf of Navid, Ryan, and Christian, have a great day. Thank you very much.